Hi, welcome to the new chapter. So, magnetism and matter. So, in the previous chapter, we actually talked about how magnetism comes across using electricity, moving charges and magnetism. Whenever the charges moved, they produced magnetic field. Now we are actually looking at magnetism as a much more fundamental concept, which was how it was first actually discovered. Okay, first the connection between the electricity and magnetism was actually made much later. Okay, by Oersted and then Faraday and Maxwell. All these people came and did the connection between magnetism and electricity. But before that, magnetism was there. Okay, it was already there in terms of permanent magnets mainly. So in the nature itself, certain matter exists in the exhibited magnetism. Now how these matter exhibited magnetism, that we will see, and how it can be related to the current that we talk about. We will see that in this chapter. It's more about that matter and magnetism. Okay, now the first point that we need to understand is that people knew about magnetism from very long back. In fact, 600 BC is documented to be actually a place in Greece, an island called Magnesia. Okay, there people were actually uh, saying that some of their shoes is basically getting attracted and get stuck on the road on where they are talking or walking. So they figured out that they had some iron nails in that, and that was basically getting attracted. So from there was a lot of magnetic uh, material there, magnets there, permanent magnets there in that place. So it's why it's called magnesia. Okay, so magnet came from that word, and the the property. What are the properties that they knew? They knew that magnets attract iron. They attract iron. Okay, and second thing, they knew that like poles repel and unlike poles attract. Repel, unlike attract. And thirdly, they also knew that they have a certain direction. That means they align when suspended. They align themselves to south-north direction. It's called directional property of magnet. And we know very well today that it is because of the Earth's magnetic field. So I will take the magnet and suspend it in moon. I will not see it. Okay, this is because of the Earth's magnetic field. And we also know, in fact, one of the Chinese kings, Huang Ti or somebody, who in 400 BC claimed to have defeated his enemy by using this property, because his chariot actually had a certain small suspended or a pivoted statue with a hand pointing always towards south. Okay, and that actually even in the lot of areas where there is a lot of mist and all the other things, fog, he was able to guide himself through and was able to defeat the enemy. That was the story. Okay, in 400 BC. So they were using already the directional property of the magnet. And then other important thing is that they can't be isolated. Poles can't be isolated. So if you have to write down the 4 properties of the magnet, which was actually there from long back and people knew, these are the main 4 properties. They can't be isolated. That means you can't cut. Now you take, for example, a magnet north south like this, and if you break it in the middle, So then suddenly this will become south, north and south, north, like this, two magnets, and these magnets again attract because like attract. So any amount of pieces that you make out of this, as small as even what you cannot see, okay, so microscopic level, even if you go, it will still actually be having two poles. In fact, if you go too much small, then you may be hitting and destroying its magnetism. We will find out why that is so. Okay, magnetism may itself be destroyed, but you cannot make two poles, two different isolate. So there are no monopoles. Okay, there are no monopoles. So that is basically what the magnetism that people knew from long back. In fact, magnetic lines of force or magnetic field, what we call, okay, so it differs from electric field. If you look at, for example, magnetic field, if I keep a magnet like this, north and south, the magnetic field actually from outside, if you see, it goes from north out and enters towards south in, like this, and inside it is going from south to north. So these are the things that you already kind of familiar with, but they are all in some closed circles. The closed loops need not be circle, they are all closed. So if you actually see here, this is how they look. So this is how a magnetic field looks like. So you can see, it's beautiful. So this is how the magnetic fields look like. You can see inside, they are all actually going from south to north, and all of them are actually closed loops. Okay, and if you look at, on the other hand, how does an electric field look like? Okay, an electric field, if I want to take dipole, because we have to compare apples to apples, in the sense that here there are two poles, N and S, so there also will take one plus Q and take minus Q, okay, connected by some internal force, so some kind of alignment to so that they don't go away, okay, or get attracted. So if you keep such a thing, it's called a dipole. And if you see what the electric field is for them, electric field is actually always from plus to minus. You can see this is how the electric field is. This is the way electric field is. You can see always electric field lines actually originate from positive and go to negative, or they originate from positive and go towards infinity, and originate from negative and go towards infinity. Okay, they are never actually closed paths, so they are never closed. So you can see here also, this is starting from here and ending here, that's all, it's not continuing. So they are not closed loops, they are always from point to point. Okay, one of the points may well be infinity, but point to point. So this is basically the difference between magnetic field and electric field. This is electric field. This is electric field due to a dipole, and this is magnetic field due to a dipole. This is a magnetic dipole. This is the electric dipole. Magnet is never available as a monopole, whereas electric is available as a single charge, a monopole. Okay, that is a major difference. And then if you want to see a solenoid, okay, so if you take, for example, a tube or a pipe, and to the pipe you basically put a wire and conduct electricity through that. So then the solenoid actually behaves similar to a dipole, a magnetic dipole, and you can clearly see that even here the magnetic field lines look almost similar. Like this. So they are all attached here. So it's same as. So these are all exactly similar to. So you can see here that this and this, that is a magnetic dipole that is naturally occurring, and a magnetic dipole that we created using a solenoid. Both of them, the field looks exactly similar, they are alike. So we can actually say that solenoid and a simple magnetic dipole like a bar magnet, they are actually exactly same. Okay. So however, let us also do some calculation on really what is the value of field strength. They may look like this, but the field strength at this point, if you calculate for this and you calculate for this, are they similar or are they different? How are they? So you can actually have a magnetic moment for the solenoid also, for this one also. Using the magnetic moment, let us actually calculate what is the value of field strength and see whether they match. So if they match, then we can say that they are both exactly same. Okay. So let's just try that attempt. So how do we do that? So for a magnet, how to do this? Let's just use our experience from electricity and see whether we can do something about it. Okay. So let's say for a magnet, you have for a plus Q and a minus Q. Minus Q separated by a distance 2L. This is our electric dipole, correct? Okay. So to the electric dipole, we actually used, we calculated the value of the field strength E. Let us say this we call the axis of the dipole. Axis of the dipole. So if you just recollect, on the axis of the dipole P, if we say from the middle point to here is the distance r, then we calculated what is the electric field here. It was very straightforward. We calculated from here. So let's say electric field due to plus Q at that point P. Okay. So is nothing but we can say 1 by Q divided by 4 pi epsilon naught into R minus L whole square. The distance is R minus L, no? R minus L. This is 2L, this is L. So this is how we calculated actually. And we also said that E minus Q is equal to Q divided by 4 pi epsilon naught into R plus L whole square. Like that we calculated. Then one of them is in this direction, one of them is in this direction. So the one which is in the outward direction here, in this case, is stronger than this. Why? Because that is due to plus Q. Okay, plus Q is repelling, so this in this direction, and for this one it is little smaller. So the difference is basically in the outward direction. Okay. So that basically is what we calculated by adding then. So we E due to E at point P, we said that it is simply calculatable by adding these two. So we are subtracting rather. So this is nothing but Q divided by 4 pi epsilon naught, and we said that it will be 1 by r minus L whole square minus 1 by r plus L whole square. Like that we calculated, and we took the LCM and everything, and finally we came to basically a simple formula. Finally Q divided by 4 pi epsilon naught, so not Q, okay, 1 divided by 4 pi epsilon naught into, okay, into, we said that 2 into P divided by R cube, where when R is very high when compared to L. This is how we calculated. I mean, you can go and calculate. One more step only I have jumped. Okay. So 2 into P by R cube, where P, okay, P is equal to Q into 2L. So we can actually, see, look what we did. We said that in the electric field on the axial line is simply proportional to 1 by r cube, and it is on the numerator we have 2p. P is nothing but electric dipole momentum, okay, dipole moment we call it. It's called dipole moment. P is dipole moment. So similarly, magnetic moment M, using that we can do the magnetic thing. So what do we do for that? We actually go there and take similarly a north south like this, and we say that here on this line we will take some P, okay, and we will again take from here length L, length R. So same kind of calculations we can do, okay, and here instead of E we will say B, and V is equal to B plus Q plus P due to N, okay, let us say, is nothing but, we will actually now give, okay, instead of 1 by 4 pi epsilon naught, it will be 4 pi by mu naught, sorry, mu naught by 4 pi. Generally, magnetism, whenever we are, when in electricity we talk about 1 by 4 pi epsilon naught, here mu naught by 4 pi, okay, and we will use pole strength. So we will use some quantity called pole strength, okay. So instead of charge, let us use pole strength. Pole strength I will give it as Qm. It's a kind of magnetic charge. No, there is nothing like that, okay. So it's just a substitute, okay, call it as pole strength, okay, and then we'll basically say divided by, similar to R minus L whole square. This is similar to this. You can see exactly similar. So the charge here is replaced by the pole strength, and 1 by 4 pi epsilon naught is replaced by mu naught by 4 pi. That's all is the difference. Now if you actually use the same thing, and for south we can calculate and then add together, and you get a B which is similarly here, okay, B will turn out to be 1 by mu naught by 4 pi, that will remain, okay, into, instead of 2p it is 2m by r cube, 2m by r cube. So what is m? Where in this case also m is equal to, if this is 2l, this will be nothing but qm into 2l, magnetic moment, each pole strength into the distance between them. That is the magnetic moment of that, okay. So like that you can see that the magnetic dipole has a certain B, okay. Now what I am going to do is that, actually this is not a, so many books actually follow this method to derive this, but from the NCERT book what they say is that it is not such a good idea to go about in this manner. Mainly the reason is there are no monopoles. So we are writing this in the assumption that there can be a monopole called N, and that causes this kind of a magnetic field. There is no monopole. So when there is no monopole, assuming that I am writing this is somewhat not such a good thing. So instead, actually, in the NCERT book, instead of going through this, they just say that by measurement they have figured out that a magnetic field strength for a magnetic dipole is simply equal to mu naught by 4 pi into 2m by r cube. This is actually by measurement using a magnet. So they got this formula. Okay. Now I actually showed you how to get that formula using our some kind of a analogy from the electric field. Okay. So there are other rigorous ways of doing that too. Okay. So now the thing is, let us not go into the derivation of this formula for the magnet, that we have already got it either through this kind of a analogy derivation or through experimentation. We got the formula for a magnetic dipole. Okay. Now let us look at the solenoid and see whether it matches with this. For solenoid we can do, so we have developed a lot of tools to work on solenoid in the last chapter. So let us do solenoid. So we will take a solenoid. So I will take one this kind of a tube, pipe basically, and on that we will put the wires. Okay. So I am going to basically take the middle of this, and from here, and I will, this is the axis. On this axis I will put P, point P at which I want to measure, because first we will do the on the axis of the dipole. Okay. So on the axis of the dipole we want to measure. Okay. You also do on the equatorial plane, okay, and get another value. So now we will do it for axis of the dipole. So from here to here, as usual, we will take it as R length. Okay, and this is our 2L. This is length L, half of it is length L, and we will take this as the radius of this as let us say A. We will take it as A. Okay. Now with this in mind, we will take one single. This is actually completely solenoid, means thousands of rounds and a winding has happened on this. Okay. So I am not showing all that. So let us take one small area here, small place where some windings are there, 10-15 windings, I know some amount of windings are there. Okay, here. So I will say that this distance from here to here is dx, and from here to here I will say is x. Why I am doing all these things? Whenever you see me doing x's and dx's and all, you must realize that I am now trying to basically write some equation and then integrate it and do it for all of them. Okay. So that is why we do that. So anyway, I will not complicate it too much. So just take a look at it. Now the thing is, for one such set of coils here, only in this area. So we know there is a formula for given one coil. Okay, one coil if it is there, the dB is equal to, we have written, actually we have found out what is the magnetic field on the axis of a circular current carrying loop. So we said that that will be equal to, dB is equal to mu naught by 2 into The formula is mu naught by 2, mu naught I by 2, I is the current, into R square by R square plus x square to the power of 3 by 2. This is the formula that we had derived earlier, okay, where these have a different meaning. This R was actually the radius and x was this length. In this case, that x has become small r and radius is small a. Okay. So, we will write it for this one single loop. So, now that will be in this case, in our case, solenoid for the number of turns in length dx dv is equal to, okay. If there are n turns per unit length, then total number of turns in this length is actually n into dx, the number of turns. This is the number of turns, n into dx. Okay. Now we have to write into mu naught I by 2. Okay. Instead of mu naught I by 2 into number of turns we have to add. This is the number of turns, n into dx. N is the unit number of turns per unit length, mu naught I into, okay, r square by, we will write that. In this case, r is actually a square divided by, okay. So let us just look at this, this part, x is r here, okay. So the length distance actually from here we have to take. This is causing what magnetic field here is what we are trying to find out. This particular coil, what magnetic field it is causing here? It will be in this direction, we know that, the dp. So that length is nothing but small r minus x, okay, the distance, small r minus x whole square plus this r square is simply a square to the power of 3 by 2. Now what we need to do, okay, that is what is our dB. Now what we need to do is, if we move x from minus L to plus L, okay, we will get this answer. What is the meaning of that? The meaning of that is basically that one small amount of dx if you take, for that much coil we produced this much dB, okay. That is the, so now if you take for all the coils, we will sum up all of them. So the sum is basically that integration is, the summing is from minus L to plus L. So we will write it as, okay, mu naught n I a square by 2. I am going to take out things which are not variables outside the integration. So inside the integration you have dx divided by r minus x whole square plus a square to the power of 3 by 2. So you will have to integrate this with respect to x and substitute the limits minus L and L to get the exact value. Okay. So it is doable. However, I am not going to do it. Why I am not going to do it? Because at this time of the when you are learning physics, you are still not learned how to do a good integration, okay, where we substitute basically over the values what you want to substitute. Through substitution, how do you get back the trigonometric functions and integrate, all that whole technique is not known. So I will not complicate it to you, okay. Instead, we will do some assumptions. What are the assumptions? Let us assume, okay, let r is very big when compared to x. In the sense what? When compared to this we are looking at this point very far from the solenoid. So which is a fair assumption to make, okay. And then also we will say r is very big when compared to a. That means when compared to solenoid's diameter, that length is very big. So if we do like that, then this whole thing goes away, the x's and a's, okay. So you will get only r square to the power of 3 by 2, which is r cube, and r being a constant can be taken out. So we can simply write it as mu naught n I a square by 2, okay, r cube, like this. And inside here what is remaining simply is minus L to L Tx. So which is nothing but dx, if you integrate you will get 1, this is like integrating 1, you get x, and substituting upper limit and lower limit you will get it as, which is equal to mu naught n I a square by 2 r cube into x from minus L to plus L. So L minus L, which is 2L. So we will get it as 2L. So this is nothing but mu naught n I a square into 2L by 2r cube. We got it as B. This is our B. Nice. So we wanted to get some B like this, but we got something else. Okay, let's just do some work around this. So what is the nothing the magnetic moment? Magnetic moment can be written as, okay, magnetic moment of a current loop, okay, M is equal to, okay, I into A, or it is N I into A, number of turns into I into A. Now number of turns actually is nothing but, in our case, N into dx, and I remains I, and A is nothing but pi A square. Okay, in this case it is, if you want to take all the n, not n just x, okay, full we are taking, nothing but n into 2l actually, okay, n into 2l into I into pi A square. Okay, that we already have on the numerator. We can see n I into A square into 2a, pi we can get it out down. So m by pi we can write it as n 2l I A square. So n 2l I A square, all of them are there. So we can simply write it as mu naught into m by pi 2 pi r cube. We will add a few more, one more 2 in the numerator and denominator. Okay, so you do that, you will get it as mu naught into 2m by 4 pi into r cube. You can see very clearly we got B is equal to mu naught by 4 pi, mu naught by 4 pi, okay, into 2m by r cube. So we were able to get actually for a solenoid by approximating it a little bit, because of the distance that you are taking here very far, we were able to actually get the magnetic field B on the axis of a solenoid will be actually equal to mu naught by 4.2m by r cube. And from our earlier arguments, a magnetic dipole, that is a real magnet itself, also has on the axis mu naught by 4 pi to 2m by r cube. So we can say that with a fair certainty, solenoid and a magnetic dipole are both same. Okay. So once we say that, we can also approximate, and later if you want you can also derive. So I am going to write here by extension, okay, on equatorial plane B is equal to mu naught by 4 pi into m by r cube on the equatorial plane here. On this plane somewhere, if you take P and this is R, then this is the formula for that, because I know of the electrical dipole. I am doing the same thing here also. Okay. So that gives us a good understanding of the similarity between a magnetic dipole and a solenoid. Okay. Now what we will do is basically we will actually put the magnetic dipole inside a magnetic field and look at what happens. Okay, what happens if you put a magnetic dipole in the magnetic field? Okay, so what should happen? Let's see. Okay, if you think about it, actually, we are actually doing exactly the same things what we used to do it for electric field. Now in the magnetic field, we were doing, okay, we will take an electric dipole and keep it in the electric field and see what will happen. So in a uniform electric field, when we kept it, we saw that it actually gave a torque, tau, and we measured the torque. It turned around. So you took basically an electric field, something like this electric field, and we put a dipole here, and the dipole turned like this in the direction finally. And initial theta we looked at, and what is the torque that it produces when you put it there. That also we found out. And the torque that it produced was simply we calculated that to be P into P cross E. Okay, it produced the torque which is P cross E, where P is the dipole moment of the electric dipole, okay, and E is the electric field. So theta is the angle between them. And similarly, we also saw that if you keep actually a small current loop inside a magnetic field, will experience a torque, and that torque, okay, if I put a current loop inside a magnetic field V, I put a current loop. Okay, the current loop is like this, means it has an angle theta, assume. So if you put it there, okay, then we found out that the torque for that was given by M cross B, where M is simply nothing but current into A, area vector. So these are the things we did in the last chapter. Okay. Now here again the same thing, there is no difference. So we are only saying that now the tau is equal to M cross B is applicable directly here in the case of the magnetic dipole kept in a magnetic field. Okay. So what we will do is, we will find out now how do you use that to measure a strength of a magnetic field. So we are going to go a little differently. Okay. So what we will do is, we will actually figure out, let us say there is a magnet here, okay, and which produces a certain magnetic field in this direction. Something like this, it produces a magnetic field. Even if you can keep a solenoid, it is the same thing. Now assume that some magnetic field is here. Okay, I am just basically writing it so that it's easier to understand. So this is how magnetic field produces. Now I will choose some area of the magnetic field and I am blowing up and showing that area. So magnetic field V looks like this. Now in such a magnetic field, if I keep, for example, one compass needle, okay, I will put a compass needle. Compass needle is a real nice dipole with an angle theta. This angle is theta, and this compass needle has a magnetic dipole moment M. Now, what is the torque that is exerted on the compass needle? The torque that is exerted on the compass needle is nothing but tau is equal to m cross p. We already know this. Tau is equal to m cross b. From the electric point of view, or from the magnetic current loop point of view, we already know that. Now, if we do tau is equal to m cross b, if I take only the magnitude of the tau, I will write it as mb sin theta. So, there is one easy way actually to measure the b at any point here, okay, the b of this, whichever point at which you want to measure b, you put the compass needle. The moment you put the compass needle, the torque that gets generated will make the compass needle actually oscillate. Okay. The oscillation frequency or oscillation time period you measure. From there you can measure the B. Okay. Measuring B using compass needle oscillations. This is possible to do like this. So, if you look at the compass needle actually, okay, compass needle that I have, so you can actually look at a compass needle. Okay, this is also a compass needle. Okay, so the compass needle has a small, very small needle on this. You can see. Okay, I cannot actually show you a horizontal thing, but horizontal is the one which you have to see. Okay, I'll just bend it a little bit, and you can see that it always actually does an oscillation. Okay, it doesn't just stay on one point; it oscillates because it is always some kind of a torque is exerted on that. If I take a magnet actually and take it near this, okay, it tends to give a certain oscillations. I am going to just put it here. It really gives oscillates. Okay, I'll just show you. Okay. So if I do it on the horizontal, it works actually because it is not supposed to work vertically. Okay. You can see that it oscillating. Let me see. Can you see this oscillation? Even nearby, maybe you will be able to see. If you watch it here, you can see that it actually, when I bring it nearby, it oscillates. It's very hard to show it because the moment I make it vertical, the oscillation stops. Otherwise, when I bring it near, it very nicely oscillates. Okay, and that oscillation like this. Okay, you can measure the time period. You can just see how many times it oscillates per second and get the time period. And from that time period, can we measure B? See, the thing is this. The reason why it oscillates is this. Okay, now this has a magnetic moment m, okay, and it wants to basically align naturally, okay, to some location. The moment you bring it here, there are two torques which are opposing. One is a torque which is basically due to this. The other one, okay, is its natural tendency to go back to the original position. Okay, so these two are actually kind of opposing each other. Okay, so the other one is due to the torque that is created, let us say, is called a restoring torque, and that is proportional. Okay, the restoring torque, let us say, is proportional to the theta that it has turned. Okay, so restoring torque okay, tau, I'll say restoring, is equal to, okay, we will write it as I alpha. What is I? Here I is moment of inertia. I am writing a stylish I means moment of inertia. So, if you remember actually last year rotational magnetism, it is rotational motion. You know that torque is equal to I into alpha is a very clean Newton's second law. Okay. Newton's second law is F is equal to ma. F is equal to m into a, because F in linear motion is similar to tau in rotational motion. Mass in linear motion is proportional, is similar to moment of inertia in the rotational motion. Acceleration in linear motion is proportional to alpha here, similar to alpha, that is angular acceleration. So, this can be written as I into, so what is acceleration? Acceleration is dv by dt generally, okay. Hence, alpha is d omega by dt, correct. So, this is velocity, this is angular velocity. However, v itself is dx by dt. Hence, we say acceleration is d by dt of dx by dt, which is written as symbolically as d square x by dt square. It is not time square, it is just symbology. To write d by dt of dx by dt, we write it as d square x by dt square, the double differential of displacement. So, here also we can write omega is equal to d theta by dt. What is angular velocity? Angular velocity is rate of change of angle, okay, d theta by dt. So, hence alpha is equal to d by dt of d theta by dt, which is d square theta by dt square. So, we can simply write here as d square theta by dt square. This is just for you to why I wrote that. Okay. Now, if you want to actually equate these two, okay, to get an equilibrium, at equilibrium, because this actually kind of oscillates around the equilibrium point like this, okay. So, when it oscillates around the equilibrium point, we can say they are equal but negative, okay. So, in the sense that this is actually opposing the other one, so minus mb sin theta like this, and this can be written as d square theta by dt square is equal to minus mb by I into sin theta. And since it actually oscillates in a very small angle theta, so we can say for small theta sin theta tends to theta. These things we have done in the last year also. Sin theta by theta as limit theta tends to 0 is 1. That means sin theta tends to theta. Okay. So, which is minus mb by I into theta. So, I want you to basically take a look at this particular interesting statement. This is a very interesting statement, minus mb by I into theta. How does it look like? Okay, let us just look at this very carefully. I am going to basically erase this side. This statement is like this, okay. This whole thing is a constant actually, d square by theta by dt square is equal to some constant, I will write some constant, okay, into theta, r is proportional to minus theta. So, you can see This is like saying that we used to have something like F is proportional, F is equal to minus Kx in a normal spring. In a spring, F is equal to minus Kx. That means the restoring force, you have a spring, okay, and it's at a normal position. Let's say you are basically going to pull it a little bit. So then it has a restoring force to pull it back. Now how much? Means if you had pulled more, it has a more restoring force. If you had pulled less, it has less restoring force. That means your force, restoring force, is proportional to how much you have pulled. That means how much was the displacement. So F is proportional to x, okay, and F is equal to Kx, but in the opposite direction, restoring force. X is in this direction, F is in the other direction. So F is equal to minus Kx signifies a spring. So and then we leave it here. It will do oscillations like this. Why does it do oscillations? We figured out last year by a simple pendulum and all the other experiments and also derivations. So if you see very clearly here, this is nothing but m into d square x by dt square is equal to minus k into x, isn't it? So this is d square x by dt square equal to minus k by m into x. And we wrote it, finally we derived it, an equation for x, or rather time period, sorry, we derived an equation for time period. We said that time period is equal to 2 pi root m by k. This is what we did last year. Why so? Because we said that this gives us what we call, this is nothing but a solution to any, see, look at what we are saying. What we are saying is we are taking x, okay, and when the x is differentiated twice, that is d square x by dt square, okay, you will get, and multiplied by minus k x by m, then you will get this one. That means you take x and multiply it by minus k x k by m, then you will get its twice differentiated value. It is very straightforward. Okay, suppose if you had sin omega t, you differentiate it 1, you get cos omega t into omega, correct? First time. Okay, so this is x, this is dx by dt. Second time you differentiate d square x by dt square. So omega into cos omega t is minus sin omega t, minus sin omega t into omega, that omega I will put here omega square. So look at this, d square x by dt square is equal to minus omega square into sin omega t. So sin omega t is x only, d square x by dt square is equal to minus omega square x. So this omega is actually angular frequency, and that angular frequency omega is equal to 2 pi f. Okay, so that means 2 pi f is equal to omega. Okay, omega is what here in this equation? It is nothing but k by m. So these are the things we did in the last year, so I don't want to complicate it much further. So we will do the same thing here. Okay, so that is somewhat easier. So let's not get back to the old one, though I think you were able to recollect it from what all I did. So this is nothing but d square theta by dt square is equal to omega square into theta, where omega square is equal to mv by moment of inertia. So omega square is nothing but 2 pi by 2 pi f whole square, or 2 pi by t whole square is equal to mb by I. What we want is b. B is equal to 4 pi square by t square into m t square, 4 pi square by m t square, that is the value of B. Okay. So, you directly get 4 pi square into I forgot moment of inertia, 4 pi square into I divided by m t square. So, that is what you get directly. Suppose if you can measure t, that is the oscillation time, and if you know the magnetic moment of the small needle and then the moment of inertia of the needle, you can simply calculate the B, okay, the magnetic field at which the needle is placed. So, any time when you have a magnetic compass needle, and if you actually know two things about this, one is its moment of inertia, second is its magnetic moment. If you know that, then this will be very useful. Wherever you go, you just put it there and count the T and calculate B. Magnetic field you will directly come to know. Okay. So, just to take one small problem, I will show you how to do that. The problem is the magnetic needle has magnetic moment of 6.7 into 10 to the power of minus 2 ampere meters. Magnetic needle has dipole moment m is equal to 6.7 into 10 power minus 2 ampere meter square, and the moment of inertia is equal to 7.5 into 10 to the power of minus 6. Moment of inertia is equal to 7.5 into 10 to the power of minus 6 kg meter square. So, it performs 10 complete oscillations in 6.7 seconds. 10 oscillations in 6.7 seconds. Calculate the magnetic field strength, find B. So, I said I have a needle, compass needle, okay, which has these two characteristics. M is equal to 6.7 10 to the power minus 2 ampere meter square, okay, and I is this. So, now 10 oscillations I count on this. Whenever I take and put it in the front of a magnetic, some magnetic field, whatever it produces, the oscillations, I am going to count, and 10 oscillations I counted for 6.7 seconds. That means per oscillations is equal to, okay, 6.7 by 10 is equal to 0.67 second, that is T. So, once you get, sorry, that is T. Okay. Once you get T now, we will substitute it here. B is equal to 4 pi square into I is given 7.5 into 10 power minus 6 divided by, you have mt square, m is how much, 6.7 into 10 power minus 2 into t square is 0.67 square. So, from this you can compute the value of B, and it turns out to be somewhere around 0.01 Tesla. Okay. So, we got a fair understanding of basically how to work with simple magnets, compass needle, and also concepts are not very different from electric fields, and we have also seen how the solenoid is same as a bar magnet, or what you call a magnetic dipole, and we also computed what happens if you keep a needle inside the magnetic field. Okay. So, next we will come back and see the magnetism and Gauss law. How is Gauss law related to magnetism? That will be our next step. Thank you.